The thin layer of soil around roots of plants is called rhizosphere. Comparing to the bulk soil, rhizosphere has different properties, and the reason is the existence of mucilage, one of the root exudates. I'm Omid, and through this video I would like to introduce you my newly developed Pore-scale model, which simulates the drying of mucilage in the rhizosphere. Studying the water solution of mucilage reveals that dilute solution forms a Newtonian fluid. By the decrease in water content, non-Newtonian behavior will emerge, and the fluid will change into a shear thinning fluid. Further reduction in water content will give us a hydrogel with viscoelastic properties. And finally, at the dry states, it becomes a brittle solid. Computational fluid dynamic tools, such as Lattice-Boltzmann method, show to be applicable and also efficient to simulate the physical behavior of this solution, from viscose to viscoelastic. However, and in the dry states, they are not useful and applicable anymore. Then we have employed a new version of lattice spring method. First, we characterize the solution using some linear springs, which are connected together using cubic arrangement. A linear relation is defined here between the stress and strain of the spring until the breaking point of the spring. Now, let's assume some of this solution as a liquid bridge between two soil particles. All of the springs are the same, and the whole network is at equilibrium state. To represent the decrease in water content and drying, which will consequently shrink the network, a tensile force is applied to the whole network. And now to recover the equilibrium state, the network has to shrink. Within the model, we do this shrinkage iteratively, and we continue this over enough number of iterations to ensure that the equilibrium is recovered. And now, by applying another tensile force, we repeat the whole process again. Now, by changing the properties of springs and defining different networks, various structures will be formed. Comparing them with the real observed structures of mucilage shows a good agreement between the output of the model and the reality. These structures will help us for better understanding the pore distribution of mucilage, which will affect the hydrodynamic processes in the rhizosphere, especially during the drying of the soil. These structures have a very important effect on hydraulic conductivity, solute transport, gas diffusion, and also the hotspots that microbial activities take place. Thanks for watching.